All right, so in this problem, we're looking for the slope at A. That's at this point here, A. Oh, that's not right. I messed that up. That should be a B. You can't. I know what the slope at A already. What's the slope at A? Zero. That would have been a quick problem. If you get that on the exam, sweet. That ain't going to happen, though. So we're looking for the slope at B and the displacement at the midspan. Everybody see that? Okay. So the first thing we do is, let's think about it. We have two tools at our disposal right now. One is direct integration. Direct integration would require one and then two sets of moment equations. And then integrating that, you would have 4 integration constants. You could do it, but it would probably be a bit of a challenge. So I think right now of the two that we have, I think conjugate beam would be more appropriate. So let's make that choice. And I'm sorry, I wrote that up high where you couldn't see it. Let me write that here, B. Now you can actually see it. So what it's going to require us to do first is to construct the moment diagram for the frame. For the beam. So I'm going to assume here at A that I have a positive shear and a positive bending moment at A. And I'm going to solve for those things and then use that information to construct my shear moment diagram. So to find my shear force and my bending moment at A, I'm going to use this as my free body diagram, and I'm going to apply my equations of equilibrium. So the first one that I'll use was I'll sum moments at A and make sure it's in equilibrium. So when I sum moments at A, the shear at A passes through A, so it won't create any moment. That's good because I don't know the shear at A. And then I'll have the moment at A. And with my sign convention being right-hand rule, that moment is going to be what? Negative. So I've got a negative moment at A, according to this sign. And then about A, I have this 8 kilonewton and another 8 kilonewton force, and they're going to create what kind of moment? Negative. So that's negative moment. Now they both have 8 kilonewtons for the force, so I'll collect those. The first one has a moment arm of 2 meters, and the second one has a moment arm of 4 meters. So I'll have 2 meters plus 4 meters. So I should be able to solve for my moment at A. It looks like it's going to be negative, and it's going to be 8 times 6, which is 48. Right? Good. All right. Now we can quickly find the shear by summing forces in the y direction, or the vertical direction. I'll make sure they're in equilibrium, and I'm going to assume up is positive, so my shear is acting up, so that will be positive. 8 kips is down. 8 kilonewtons. 8 kilonewtons is down, so I'll write those in my equation this way. So it looks like the shear at A is positive and equal to 16 kilonewtons. So with that information, I can come over here and I'll construct a template for my shear moment diagram. So I'll have a starting point and end point. I also recognize that at this point load, there's going to be probably a change in shear, so I'll include that in my my template also. So then I'll go ahead and assume, I'll show my positive x-axis, and I'll assume that positive shear is up, and all of these will have the units of kilonewtons. So what is the shear at A, our beginning point? Well, we solved for it. It's 16. Positive 16. So I'll start at 16. We know the change in shear is equal to the area under the load curve, and the area under the load curve is 0. So that means I stay at 16. I also know that the slope of this line, whatever it happens to be, is equal to the load at every point. And the load at every point is 0. So 0 slope means a horizontal line. So we know now that we have constant shear of 16 kilonewtons over the first 2 meters. Now as we go from the left side to the right side, how much does the shear change? Well, it changes exactly the amount of the load, which is 8. And that's a positive or negative load? Negative. So it's going to drop 8. So 16 minus 8 is 8. So the change from the midpoint to the right side to the end, that change in shear should be the area of the load curve. Area of the load curve is 0, so no change. So I'm going to end at 8. And of course, the slope of this line is given by the load, and the load is 0 everywhere. So a curve with 0 slope is a horizontal line. So I get a nice little step function for my shear. And my shear of positive 8 at the end here matches the shear at the end of the beam. So that's good. So now we'll begin to construct the moment diagram. So again, I'll indicate positive x, positive moment. All these units will be kilonewton meters. And let's see what we have to start with. Well, I know the moment at A. I solved for it. So I have a bending moment of negative 48. What's the bending moment here at B? 0. So I know where I'm going to start. I know where I'm going to end. Let's see if we can connect the dots. So I know the change in moment between 2 points is the corresponding area in the shear diagram. And what is that area in the shear diagram? This is 2 meters, by the way. So 16 times 2, because it's a rectangle, base times height, is 32, and that's positive area. So 48 plus 32 is 16, right? What's the slope of the curve between these 2 points? Well, the slope at every point is given by the value of the shear. The value of the shear is constant everywhere, so it's a constant slope, and it's positive. So you get a trapezoidal load shape. Now the change in moment between 2 meters and 4 meters is the area of that portion of the shear diagram. I'll double hatch that one just so you can see that it's a little bit different. So that's going to, again, a rectangle. The area of the rectangle is 2 base times height 8. That's 16. That's, again, positive area. Negative 16 plus 16 gets us to 0. That's great. What's the slope of the line? Well, the slope everywhere is given by the shear, and the shear is constant and positive. So I get a constant positive slope. So now I have this kind of triangular shape, trapezoidal over the first 2 meters and triangular over the last 2. So there's our moment diagram. So that's part 1, basically. So part 2 is now we're going to construct the conjugate beam. What is the conjugate beam? You might recall from our discussion last Thursday and even on Tuesday, past Tuesday, that we know that a real fixed connection is what in conjugate space? Free. And therefore a free in real space is what in the conjugate space? Fixed. So it looks like the beam is going to kind of just flip around. Now remember, that's not a good analogy. I don't want you to think the beams just always flip over and mirror. That's not the way it works. Remember, fixed becomes free, free becomes fixed. In this case, it does look like it inverts, but that's not the pattern. And now I'm going to dump this load, this moment diagram, on this beam. So again, what I like to do is I just like to literally transfer it. Just move the shape right over. If this were an animation, I'd somehow cut this out and take it and just go, boop, drop it right on there. So it almost looks like the moment diagram, but there's just a beam on top of it. That's what it is. So remember, conjugate beam, we load the conjugate beam with the moment divided by EI. And that maximum value here is 48, and that's kilonewton meters divided by EI. And this value is going to be 16 kilonewton meters divided by EI. This moment is all negative. So which way is a negative load? Up or down? Down. So you end up with something that looks like this.
Oh. Quick question. If I wanted to leave EI just out all the way to the end,
you can do that. Just have to remember to bring it back at the end. Don't lose it. And you'll notice here I didn't give you a value of E and I, so we'll have to just assume that E and I is constant. Okay, so what do? Now, the question says, what's the slope at B? Well, the slope at B would be what in this beam? It would be the shear. So I need to find the shear at B. That's the shear in this connection. Remember, shear, positive shear, is down on this right-hand side. Okay? So let's do that first. So all I have to do is find that value. There's, by the way, there's going to be a moment there too. What would the moment at B give us? It'd give us the free end displacement in the real beam. Unfortunately, that's not what's asked for. That'd be a good question for the final, though. I mean, and for the next test, because you could get both those results with this one free body. This problem, though, it wants the displacement at the midspan. So we're going to have to come over here and cut this structure at the midspan, and you're going to have to decide to use the left side or the right side. And we'll talk about that when we get to that. But first, let's solve for the shear. So how do we do that? Well, I got a lot of things I've got to resolve here. I think it's going to be easier for you guys if you look at this as three different loads. A little triangular load, a little rectangular load, and then two triangular loads. And the height of that rectangular load would be 16. What's the height of this triangular load? It'd be 48 minus 16, it'd be 32. So I'm just gonna sketch them in there. So I'm going to call this first one F1. I'm going to call the one associated with the triangular piece F2, and then the one associated with this smaller triangular piece F3. Just notation. And sometimes that orange doesn't do well in the visual, so I'm going to now just use my black ink to calculate those. So let's do F1 first. What is the value of F1? Well, it's the area of this part of the curve. It's a rectangle, base times height, right? So that'd be 2 meters times 16 kilonewton meters over EI. So that's going to be 2 times 16 is 32 kilonewton meters squared divided by EI. Everybody see that? What about F2? That's this part. That's a rectangle. That's a triangle, so that's going to be 1/2 base 2 times height 32. Well, the 1/2 and the 2 cancel, and you just end up with 32.
Wouldn't it be negative?
Well, I've indicated the direction by saying they're down. The magnitude is this number, but they're acting down. So again, so it's going to be 1/2 base, which is 2 meters, times height, which is 32. So the 2's cancel, you get 32. And now F3 is this triangular shape. And of course, every triangle gives 1/2 the base, which is 2 meters, times the height, which is 16. Again, the 2's cancel, you get 16. So those calculations are not too bad. Now, if I'm just going to go for the shear, do I care where those forces are positioned? I do not. I'm not taking moments to find the moment at B, which could be a problem. That could be a question I ask you. What's the displacement at B? But in this case, the end, I don't need it. So I'm just going to go straight into summing my forces in the y direction, vertical direction. I'll assume up is positive. So here, Mr. Zacher, this is where your question comes in. All these forces, F1, F2, F3, are down, so I would say those are negative. And the shear at B is also down, so that's also negative. So I'm going to have negative the shear at B and then minus these three forces. 32 kilonewton meters squared over EI. There's one of them. Then again 32 kilonewton meters squared over EI. And then the last one, 16. So it's pretty easy, I think, to calculate that the shear at A is going to be negative, and it's just 32 plus 32 plus 16. Did I do something wrong? Oh, you're right. I'm sorry. Let me try to turn my A into a B. Thank you. So what is that, 80? So 80 kilonewton meters squared divided by EI. And it's negative. Now remember that is going to map back into, this is the shear at B in the conjugate beam. What does that map back to in the real beam? Shear maps to slope. And that's what we have. So it's negative. Does it make sense that I have a negative slope at B? I think this is not the exact displaced shape, but you are going to get some shape like that, right? And I think you can see that if you looked at the slope out here, that is a negative slope. So that sign matches. You'll also notice that the numerator value here is pretty small. So when you divide that by E and I, which are pretty big, you're going to get a very small angle, which seems reasonable. Any questions about that? Okay, so how do we solve the second part of the problem? The displacement at the midspan. So that would be the displacement at the midspan in the real beam is what at the midspan in the conjugate beam? Moment. So now we're going to cut the structure here in the middle. And you want to work the right side, the right side or the left side? Okay, let's talk about that. So we work the right side. I'll block that off. What do I need to know? Well, I've got the shear. I don't have the moment, do I? So now I've got to go solve for the moment. I can do that. What if I work the left side? What do I need? I don't need any moment. I don't need any shear. I don't need any previous calculation. I just need to work with two forces and those distances. And I already have those forces. So I think the left side is better. Because to find the moment on the right side, I'd have to deal with three forces and their moment. Just to get the moment, right? And then I get to cut it. But if I cut it here first and look at the left side, I just deal with the moment of two forces. So I'm going to cut it here. I'll try to put a line, and I'm going to say I'm going to go left. So I'm going to come down here and redraw that. See if I can squeeze it in here. So there's my left side. Remember, this thing was 2 meters long, and then I'll transfer onto that those forces I had. You might recall that this one was 16 kilonewton meters divided by EI. This one was 48 kilonewton meters divided by EI. And those forces are down. And then at the cut section, I would have my positive shear and my positive bending moment. And all I'm looking for is this bending moment. So again, I think we can go back just like we did up here, and we can split this into two distributed forces, just like we did before. In fact, we've already calculated them, F1 and F2. If you look again, we already have F1, and we've already computed what I called F2. Now, from the cut, I need to know their position, so I'll need to know the distance. I'll call it D1 from the cut to F1. And I'll also need to know this distance here from the cut to F2. So what are those? I think if I look at D1, I don't think that one's too bad. For the rectangular section, where's the centroid? Half the distance, right? Half of the distance is 2, so that's just going to be 1 meter. D2 is the distance from the small end of the triangle to the centroid. That's 2/3 the distance. And 2/3 of 2 is 4/3. Right? 2 times 2/3, that's 4/3 meter. I just didn't want to write the 1.333333. I'll just write it as 4/3, and I got it all in there. Anybody happy with that? So now all I have to do is sum my moments again, this time at the cut surface that we just created. That would be the midpoint. And let's see what I've got going on here with moment. So again, using right-hand rule for my sign convention, my moment here is what? Positive or negative? Positive. And about the cut, F1 and F2 create what kind of moment? Positive or negative? Positive. So we'll do F1 first. So we know F1 is 32 kilonewton meter squared divided by EI. That's the force. And then times D1, which is 1 meter. And then F2, F2 is also 32 kilonewton meters squared divided by EI, and then times the distance from the cut to that force, which is D2, which we've calculated as 4/3 meters. So I solve for the moment. It looks like it's going to be negative. And before I even do the calculation, being negative means what for the displacement at the center? It's up or down? Down. And I think that looks good. I would expect the center of this beam to go down. So that matches. So now I've just got 32 plus 32 1/3, which is going to be some strange number. So you guys have to help me with that.
I got 224 over 3.
That sounds too high.
74.67.
That sounds better.
That's the same number.
Well, oh, you said over 3. Sorry, I missed that part. When you said 207, I said, oh, that's too big. So what is it again? Give me the fraction form. 74.67, and that'll be kilonewton meters cubed over EI. Okay, that seems reasonable to me. So any questions or comments about that one? I think that's a very, that type of problem is, I think, more typical of what you would see on the exam. Now remember, let's just do a little review. The original problem is given. I would just give you exactly what you see there. There would be no, hey, use conjugate beam method. There would be no, oh, use direct integration. They would just be, do the problem. So you'll have to kind of take your skill set and what the problem, kind of how you can classify the problem and try to pick the right method, the most efficient method. Next Tuesday, we'll introduce another method that could also work this problem. So you'll have 3 to choose from. You'll have to decide which one is best for you. Direct integration would work here, but I think it would be troublesome. So I think conjugate beam works best for this problem, because it relies on skills that you should be pretty solid at. Shear moment diagrams, finding shear and moment at a point, those are pretty fundamental. I was talking with one of your colleagues yesterday who's taking statics, and they're working the same problems in statics right now. And I know you work the same problems again in mechanics and materials. And here we are a year later working the same problems in structural analysis. I think they may be important if you see them so many times. Well, at least a structural engineer. If you're a transportation person or you love environmental, you're tired of shear moment diagrams. You're just ready to move on to something else. Maybe something with a virus or a bug in it. Water. Yeah, something you can actually consume. These are not very consumable. All right, any other questions?